Hello everyone, this is Hailey. She will be giving us a topic on thermocouple time constants.
Hi, I'm Hailey, and I am the reporter for Group 3, and I'll be talking about thermocouple time constants. So our objective was to graphically record the thermocouple time constant using a 1/8 type K thermocouple probe by both inserting it and removing it from either ice water or boiling water, which in our case today we are going to talk about the boiling water one. What is a thermal time constant? It's the time it takes for a thermocouple to change 63.2% of the total temperature, which that total temperature is from the initial to the final. And this happens when a step function occurs under zero power conditions. For this experiment, we use lump capacitance method, which is a common approximation in transient conduction, and it can be used whenever the heat conduction occurs within an object a lot faster than the heat transfer across the boundary of the object. This method reduces thermal systems to a number of lumps, and the two main assumptions are that there's no temperature gradient within the solid, and also another one is that the resistance to conduction within the solid is really small compared to the resistance to heat transfer between the solid and the surroundings. Here it is the energy balance equation, and this is after transient energy analysis is done to it. And then once you integrate the equation using initial conditions, you get the following one. Our apparatus that we used for this experiment was a 500 milliliter flask with either boiling water or an ice water. We used the hot plate to boil the water. We had a type K thermocouple, which was stainless steel sheath. We had paper towels to wipe off the thermocouple with, and also a computer system with PDAQ data acquisition capabilities. Ways that the thermocouple can change. The thermotime constant is affected by the medium that it's performed in for the experiment. So it's going to be shorter in moving air than it's still air, and also shorter in moving water than it's still water, for example. Also, the larger the physical size of the thermocouple is, the longer the response will be. And there's also many other factors that you can take into account, like thermal conductivity, thermal mass, the surface area to mass ratio, and also the stem conduction of lead bars. For the insertion, we use this normalized temperature equation, with temperature being just the temperature at time t, and then T infinity is going to be your temperature of your convective medium, which in our case is boiling water, and our T naught is the temperature of the thermocouple, and we'll use that equation to find that normalized temperature. These are just our two graphs for the insertion. The first one shows the original temperature versus time, and the second one is once we normalize the temperature versus the time. And then our last analysis that we had to do was with the normalized temperature, the natural log of that, which you can see the equation up here, and we got that it was 0.7391, and you can also see that it's determined from the slope of the linear fit line also, which you can see here. For the removal, we did the same process, the same normalized temperature equations, and these are the results we got for that, the original temperature versus time, and then the normalized temperature versus time. And also, we got the time constant be 62.681 for this, which was also the slope of our linear fit line. We compared it against the ice water, which was, they got 4.14 for their insertion and 64.17 for their removal, which, as you can see, both the insertion is a lot smaller than the removal for both cases, and this is because the density of water is a lot higher, so that plays a role in like the heat coefficients and the time constant. And with that being said, putting something into a water is going to transfer heat a lot faster than taking something and just putting it into the air. conclusion, overall, the time constant can vary in many ways. There's a lot of things that affect it. Many material properties like thermal conductivity, density, like I said, specific heat, constants, and things like that. And also the densities of the air and water play a big role. The reason that the thermocouple must be dried off when you remove it from the water is because you want the first thing that it takes into account to be the air around it and no water. And then also, to make this experiment more accurate, we could have done it a couple more times just to get more numbers and stuff. But overall, that's all I have for today.